Okay, let's get started. So yeah, let's review what we covered in our last lecture. In our last lecture, we talked about three topics, right? The first one is that we'll give you an example about entropy, right? And in particular, we talk about the binary entropy function, right? So if I have a random variable that takes 0 or 1 with some probability, then we can compute the entropy function, right? And then we talk about self-information, and then we talk about the property of entropy. Okay, after that, we introduce you the concept of joint self-information, joint entropy, right? So basically, the idea to define a joint self-information and joint entropy are pretty much the same as that for self-information and self-entropy. The difference here is that instead of considering only one random variable, we consider more than that, right? So in particular, we talk about two random variables here, okay? And because of these two random variables can be correlated, or they can be dependent on each other, right? Then so we introduce the concept of conditional self-information and conditional entropy, okay? And we didn't talk about chain rule yet, but we're going to talk about that today, okay? So this is a definition of entropy, so hopefully everyone now can remember it pretty well. So if you consider a random variable x that follows a Bernoulli distribution with parameter p, so this p could mean that the probability that x take a value of 1, that equals to 1. Oh, sorry, that equals to p, okay? And then by using this formula, so we can get the entropy function, the binary entropy function as this formula, right? We denote that by this notation, okay? So yeah, because this is very often used in our class, right? So we'll give you a special name for that, okay? And then from here, you can see this is a very simple function. So p is a variable here, right? And everything else is given. Therefore, so we can plot it, right? So if we plot it, so we can get this is the shape of the function, okay? And here we can see that when p equal to 0, so the entropy is 0. When p is 1, the entropy is 1, which cannot make sense, right? Because there's no uncertainty, right? And when p is half, so we reach the maximum value of the entropy function, right? That gives you 1, right? Which cannot make sense as well. Okay, so here, so we just have a very intuitive explanation for the entropy, right? It represents uncertainty, right? But later on, you're going to see that. We're going to mention a little bit today, but later on, you're going to see that. So actually, the value of the entropy means the smallest number of bits that you can represent a random variable. Okay, for example, let's say if the probability is half, then the shortest length of number of bits to represent this random variable is basically 1 bit. And here the 1 bit is the same as the bit we normally mentioned, right, like 0, 1. Okay, but if the p is not a half, or like for example, if p is 0.1, so we can represent this random variable way more efficiently. Right, you can see that when p is 0.1, then it's like the entropy is less than 0.5. Okay, the meaning of that is that on average for each random variable, we can use like less than 0 bit to represent it. It's shorter than 1 bit. Okay, so yeah, so we're gonna talk about that in detail in the later part of the class. When we talk about compression, you'll see why. Okay, but we're gonna mention that a little bit today. All right, so then we introduce you the definition of self-information, right? So self-information is nothing but this function, okay? And if we look at that closely, so this is nothing but this part, right? And of course, with the negative sign, right? And entropy is nothing but an expectation of the self-information. Okay, so the meaning of self-information is nothing but the uncertainty of each outcome x, small x. Okay, so it represents uncertainty of each outcome. Okay, so if we do expectation of it, or we do an average of it, then it gives you the entropy. It basically means that entropy is an average concept. On average, so this is the total uncertainty. Okay. All right, so, and there's some properties of entropy. First, the first one is that entropy is bigger than or equal to 0. Okay, it's always a positive. Okay, and we proved that in class. And the second one is that the highest value of entropy is less than or equal to log base 2 and the cardinality of the set X. Okay, and we're going to prove that later, so this is also relatively straightforward. And one thing to be noted is that, so if and only if X is a uniform distribution, then this equality sign will hold. Okay, so it basically means that when the distribution is uniform, then we reach the highest entropy, which kind of makes sense, right? If it's uniform distribution, we really have no idea. Oh my God, I didn't record it. You know, what a good thing. So basically, for this recorder, I have this here, like this road thing. So it automatically records in the transmitter. Okay, even if I don't plus the recording sign. Okay, therefore it's still 32 bits. Okay, so we're good. Okay, very useful. So, okay, so very nice. Okay, next is the joint self-information and the joint entropy, right? And as we said before, so definition is pretty much the same, right? No big difference. We just, instead of one random variables, we consider two random variables. Okay, that's it. Okay, then we have our self-information like that, and then if we do expectation on that, then we have our joint entropy. Okay, because joint entropy is entropy, then we know it is bigger than or equal to 0. Okay. Yeah, this is pretty much the same, but because now we have two random variables, right, then, we can study the relation between them. Okay, then we introduce you the concept of conditional entropy, right? So again, give you the distribution of x and y as px and y, right? And then we define the conditional self-information as this function, right? And here, instead of the joint distribution or instead of a marginal distribution, what we use here is a conditional distribution, right? Given y, okay, and then what is the probability of small x, okay? And then similarly as usual, so we do expectation here, then we can have our conditional entropy, right? So here we need to be a bit more careful here because now the expectation is over both x and y, right? So if we do the expectation only on x given a specific value of y, then we need to say here y equals to small y, right? So this is an average over both x and y. Okay, just be more careful on that. So here is still conditional entropy. It's a conditional distribution, right? And then, of course, the entropy is bigger than, conditional entropy is bigger than or equal to 0. Okay, and yeah, I think this is where are we in our last lecture. So now let's see what we're going to cover today. Today is our lecture number 5, okay? And today we have a few topics. The first one is still the conditional self-information, conditional entropy, conditional entropy, and we're going to talk a little bit on the chain rule for entropy. And later on, you're going to see that we have a chain rule for almost all the information theoretic concepts in this class. Okay, so this is the first time we see that. Okay, and secondly, we'll talk about the mutual information. Okay, and after that, so we're going to introduce you another important concept, which is called relative entropy or KL divergence. Okay, so we're going to talk about that later. So who heard of KL divergence? Okay, who heard of cross entropy? Yeah, it's pretty much the same thing, right? Just a constant difference. Okay, and so if we can do that, and then we'll do some discussion there, right? So we're going to talk about the relationship between them. Okay, so we're going to talk more on the chain rule. So we're going to introduce you the chain rule for each of them. And we're going to talk more on mutual information. Yeah, because mutual information is something that is extremely important and it's a weird animal, right? So we're going to see some examples of it. Okay, so who heard of mutual information? Okay, yeah, great. So yeah, let's see. All right, so yeah, let's recall the definition of conditional entropy. Yeah. Again, so we need to be careful here. So the average is on both x and y, right? Okay, very good. Yeah, this is the definition, right? Let's do some manipulation of it, right? Because, computing this can be pretty hard, right? We need to evaluate the point of each conditional distribution and the joint distribution, right? Let's see whether we can have any easier approach to compute that, or see what is the relationship between this conditional entropy and the entropy and joint entropy. Okay, so let's see. Let's derive it. So okay, the first step is that, so now we can see that we have a conditional distribution here, right? By using the Bayes rule, right? So this guy basically equals to Pxy over Py, right? So let's plug that in, see what will happen. Okay, so if we do that, so basically we are going to, here y should be in y, right, not the x. Calligraphic y. Okay, and then log here, we should have py in the upstairs and pxy in the downstairs. Okay, so if I have this fraction here, then because of log, so we can separate those, right? So basically now we have this pxy log py, right, and then minus pxy log 2 pxy. Okay, very good. Okay, so now let's see, right? So did you see anything familiar? So what is that? Right, pxy. So inside is pxy, outside is pxy, and then we sum over all of them. So that is what? Say it louder.
The joint entropy.
Joint entropy, right? So hopefully still remember it. Just joint entropy, which xy. Okay, very good. And now let's do some manipulation in the first one, right? So for this guy, okay, so you can see we have a y inside, right? And we have x outside, right? So then we just do the summation over x first, right? See what do we get, right? So then this guy equals to, right, if we just do the summation over x first, right, because there's nothing about x inside the log, right? Here we just do a marginalization of this p, x, and y, right? So sum that over all the x, that equals to the probability of y only, right? It's a marginalization, okay? And then we have log 2 py, okay? So that's what do we got, right? Yeah? Okay, what is that? So can you tell me what is that? Does that look familiar? Yeah, what's that? Yeah, minus hy, right? Okay, therefore, from here we can see that, so the entire thing equals to hxy minus hy, right? Okay, so now this is kind of important. So now we have this formula. So hx given y, so equals to hxy minus hy. Right, any questions so far? Yeah, are we all good? Okay, so if we're good, then yeah, let's continue. So basically we can say, right, that in another way, right? So the joint entropy will equal to hy plus what? Hx given y, right? So now I hope all of you can remember that. It's really easy to remember, right? How do you remember this? Just a Bayes rule, right? So Bayes rule is like px y equals what? Py times px given y, right? So this is a Bayes rule, and so this is coming from the Bayes rule, right? Because of the log, so instead of multiplication here, we just have a plus here. Right? Can you remember it? Yeah, that is very important, right? So later on, we're going to see something very similar, but not this. Okay, so here, take y out, and then we have x given y. So y is here, given. Okay? All right, so yeah. So this relationship is called chain rule. Okay, so because this is for the joint entropy, right? We say it's a chain rule for entropy. We're going to have the chain rule for many other quantity later on. Okay. Okay, so you can see that although we call that chain rule, but we have only two terms here, right? So which is not very interesting. So now we can generalize it for arbitrary number of random variables, okay? So we can generalize it. So we have a generalization of chain rule, right? So now we introduce a new notation here. So if we write like this, x power n, so this basically means a vector of random variables, okay? From x1, x2 till xn, okay? Bunch of random variables here, okay? And here, so by using this relationship, right? So basically what we can get is something that is very easy to remember, right? So what we do is the same as before, like this, right? So what we do is that we take the first guy out, right? And then we're going to have something of everything else conditional on the first one, x1, right? And then we'll keep doing this. Eventually, this is what we can get, right? So if you cannot really see it, just, do the derivation from the definition or, compute it from here. So it's pretty easy to see that. So we have x2 given x1 plus hx3 given x1, x2 plus, and so on until the last step, which is xn given x1 till xn minus 1, right? So this is what we can get, okay? Yeah, obviously you can write them together. So basically this equals to summation that I from 1 to n. So we have hxi given x1 until xi minus 1, right? Okay, and then we have this notation, right? So we could combine that. So this equals to I from 1 to n, hxi given xi minus 1. Okay, so this is a chain rule for entropy, for joint entropy. Okay, any questions so far? Yeah, this should be relatively straightforward. Okay, so now let's do some discussion here, right? Okay. So we need to know that, in general. So what do you think about this guy, hy given x and hx given y? So do you think there any relationship between those two quantity? So meaning, are they should be the same, or should each one bigger than the other one, or vice versa? So first, let's think. So should they be the same? Are they equal? No. Why not? Yeah, they're not equal. So we're going to see that later, very soon. Okay. So they're not equal. Okay. But one quantity is indeed equal. Okay. So actually, if we compute that, so if we do, like, say, hy minus hy given x, and hx minus hx given y, so these two quantities are equal. Okay, so the way we prove that is very easy. We just need to expand it using definition, and you are gonna see they are the same formula. Okay, it's like Bayesian rule, right? So if we expand it in one way or the other, okay, so so you can show that very easily, and then later on we're gonna see that. So this is a kind of an important quantity, right? I don't introduce you that now, but you're gonna see that later. Remember the formula, okay? I may ask you later. Okay, and because they are equal, and hx and hy may not be equal, therefore this and that are not equal, right? So that makes sense. Okay, and the next thing is that how about the entropy of x given x? So what does that equal to? Right, like a weird case. What?
0.
0, right? That makes sense, right? They're true. Why 0?
Because the probability of x happening, given we know x is happening, is going to be 100%.
Exactly.
So there's no uncertainty.
Yes, exactly, right? So basically, your name is Jilang?
Yes.
Yeah, so yeah, he basically give you the proof, right? But intuitively, it makes sense, right? So if we know x, of course, there's no uncertainty about x anymore, right? That's why it's 0, right? So remember, entropy is uncertainty, right? But let's repeat it. So the proof Jilang just said, right? So basically, it's an expectation of self-information x given x, right? So when we compute the self-information, let's say for each of outcome x, right? So this basically equals to what? Log 2 1 over px given x, right? Clearly, this is 1, right? If we know x, obviously x is x, right? So therefore, log base 2 1, that will be 0, okay? Then if we do expectation of that, clearly that will be 0, okay? Very nice. So that's good. Okay. So next, let's introduce you mutual information. Okay, so when we talk about the mutual information, because the mutual, right, means at least we need to have two things. Okay, so again, we need to consider two random variables, x and y. So we assume the distribution of that is px and y. Okay, so what do we do is as following. Okay, so basically now let's see. So let's say if we know nothing about y, and then we're gonna see how much we know about x. Or if we know something about y, and then how much we know about x. Okay, so we need to observe x. Let's say. Okay, our goal is that we observe x. Okay, based on whether we know y or not. Okay, so the first thing is that, okay, let's say if we know nothing about y, right, basically means that if we don't know anything, right, then the uncertainty of each outcome of x, right, let's say each outcome of this x would be ix, right, so that's the uncertainty for this outcome of x if we know nothing. Right? Okay, so now let's say if we know y is happening, capital Y equals to small y, that is happening, right? If this is no, then what is the uncertainty about x? Right? What is that?
Is it I of x given y?
Exactly, right? So that's exactly the meaning of it, right? If we know y, then what is the uncertainty of x, right? So now let's see. Okay, so this guy is uncertainty of x. So this guy is the remaining uncertainty of x if we know y. Then how much information we gain? Right? If we from not knowing y to knowing y, how much information we gain? Or how much uncertainty it is reduced? How to compute it? Yeah, now you know this, and you know that. Then what is, how much information we gain, or how much uncertainty we reduce? It is
the joint.
Joint meaning?
Like the joint entropy.
Joint entropy is uncertainty of x and y, right? It means that we know nothing.
Is it just the difference between them?
Exactly. That's the difference, right? So the first guy means that we absolutely know nothing, right? This is the uncertainty of x, right? If we know y already, and this is the remaining uncertainty of x, right? And the difference between them is the information we gain, or is the reduced uncertainty. Does that make sense? So this is something that we do know, okay? And this will give you a new notation of it. It's I of x semicolon y. So this semicolon is very important, right? So in information theory, so we need to be very careful on that, okay? So this is called, yes?
Is this related to what you mentioned earlier, when you took the joint entropy and you subtracted the entropy of y from that?
Not really. Yeah, not really. But it's a very good question. Of course, somehow everything is related, but the meaning is different, right? So here, so for the joint entropy, you can read from this formula, right? It's the uncertainty of y plus the uncertainty of x if we know y. Right? So, or, the uncertainty of y is equal to the uncertainty of x and y minus the uncertainty of y knowing x, right? So, but this is slightly different from what we're talking about now. Okay, but definitely related, right? So now what we're talking about is how much uncertainty that is reduced by knowing y.
By knowing a particular, by knowing the value of y.
Yeah, knowing a particular value, exactly. Now we're talking about the particular value.
Yeah.
Does that make sense? Okay. Yeah, kind of confusing, right? But yeah, let's
Well,
dig.
it seems like with the entropy, it's not about knowing a particular value of y, because you're summing over
Exactly.
all y.
Exactly. Right now here we'll go there. So now we just talk about particular outcome, 1y, 1x. Okay, this is knowing a particular y, then what is the uncertainty reduced for a particular x? Okay, right? So this is called what? Self-mutual information. It's not mutual information yet, right? Yeah, you may guess what is mutual information, right? It has to be some averaged thing, okay? Right, let's write it down here, the meaning of it, right? This idea is very important. So this is the information of uncertainty information of uncertainty of outcome. Okay, yeah, sorry, I do something wrong here. Is a reduction of uncertainty, not information of. Is a reduction of uncertainty of outcome x if y is observed or known. Okay? Okay, so now let's write down the formula carefully here. So Ix, yeah, now be careful here. So we need to use the smaller case, right? Small case, lowercase. So that's x minus ix given y. So let's plug in the definition, okay? Minus log 2 1 over px given y, right? And now, again, so we're going to use base rule to expand px given y. So then we have this. So here upstairs we have py, and downstairs we have pxy. Right? And then, so, yeah, because we have minus sign here, then we can combine them, right? So it's this guy divided by this guy, right? Then we have log, upstairs is pxy, and downstairs is px and px and py. Px and py. Okay, very good. All right, so this is the self-mutual information. Okay, and so you can see, it's totally symmetric about x and y. right? If you you permute x and y, then you're gonna get exactly the same thing, right? So this is very important. So it means that we have this commutative property of self-mutual information, right? Ixy equals to Iyx. Okay, so yeah, that's very nice. Okay, so this is self-mutual information, right? So next, so if we do an expectation of it, then we're gonna get other stuff, right? So again, now I have two random variables here. So when we do the expectation, we need to be careful. Okay, so what we can do here is that we can do an expectation over just x, right? We have capital X here and small y here. Okay, and here, so when we do that, we'll give you a new name, okay? New notation. We use I to represent the expectation. So it becomes Ix semicolon and y equals to y. Okay, and that equals to what? So so inside is this guy, right? And then the average is over x only, right? So we sum over this over x, and then the probability would be what? Px given y, right? Because it's like we know y, then we average it over x, right? We need to multiply that with a conditional probability. Okay, that's very good. So yeah, so this is basically what we got. Okay, and remember this guy is nothing but Ix y. Okay, so similar as before that we did for the conditional entropy, right? We can take another expectation over y here, right? So let's say if we take another total expectation, okay, of Ix and y, right? So now both x and y are capital. We consider both of them are random variable, right? Then what we can get is as follows. So basically let's write it here. So basically this guy equals to y in y, and then we copy, I need to write probability here, right? So p y, and then we have whatever we got before, right? P x given y log this. Okay, very good. Okay, and again, so because this y and this x given y, so that can be combined to a joint distribution, right? So then eventually what we get is this double sum. And then we'll have this pxy, and then log 2 pxy divided by px py. Okay, and then we're done, right? So this guy is called Ixy, and this is called mutual information, right? So this is mutual information. Okay, so again, so mutual information between two random variables, they are like, again, an averaged concept, right? It's an average on both x and y of the self-mutual information, okay? So the meaning of that is pretty much the same, right? It's an average of, uncertainty reduction about x if we know y. Does that make sense? Okay, so later on we're going to see some specific meaning of it, right? So actually, the number here again, so that is very, very meaningful. So we're going to use that to quantize, to characterize some very important, concept in terms of number of bits. Okay, so this number indeed makes lots of sense. Okay, but we're going to see that later. All right, so any questions? Yeah.
So if I use the I capital X semicolon capital Y equal to the I Y semicolon X? Like, if this switch the X and Y are the same.
So yeah.
So if the expectation of I capital X semicolon Y, right? If this switch the position of X and Y.
Yeah, that would be the same. Yeah, so yes, it's a very good comment. Yeah, because whatever inside is commutative, right? Then mutual information is commutative as well, right? This equals to I Y given X. Okay, very nice. All right, so now let's do some manipulation here, right? So we know that, again, computing this kind of formula is kind of complicated, right? So let's say if we know the entropy, can we compute the mutual information easier? Because you can see, we can observe some entropy terms here. Okay, so let's do it very carefully. So yeah, we know that this equals to the expectation of self-mutual information. Okay, and we also know that the definition of the self-mutual information is what? Is the self entropy of X minus the self of entropy of X given Y, right? The conditional self-entropy, okay? And then if we separate those two, minus expectation of I X given Y, right? So what is the first term? What that equal to? Expectation of the self-entropy. Entropy, right? Very good. And then what is that? The conditional entropy, right? Okay, therefore, so we have a very nice formula here. So basically, the mutual information equals to hx minus hx given y. Right. Again, the meaning of that is kind of clear, right? Hx is uncertainty of x, then we subtract by the uncertainty of x given y, if we know y, and then, so this is the uncertainty reduction, or this is how much information we know, we get by observing y. Okay, so intuitively this can make a lot of sense, right? For example, let's consider a communication system, right? Let's say if I transmit X, right, and through a channel there, right? There is some noise in the channel, some randomness in the channel, and then you receive Y, okay? And then, your goal is to decode X, right? Because you want to know what is transmitted and how much you can decode there, right? How much you can decode, you can get by observing Y for X. So that's basically mutual information, right? Intuitive, that makes sense, right? But later on, we're going to show that this is indeed the case. We can show that mathematically, but I'm telling you the intuition. So this is one application, right, in the communication system. Right, in this way, we can characterize exactly how much we can transmit. Does that make sense? Sort of. And another example of that is compression, right? For example, let's say I do a JPEG compression. Okay, it's lossy compression. It's not lossless. Right? So I have original information X, right? And then let's say if after compression, I have X hat, which is not X because it's lossy compression, right? But how much information you know by observing X hat is mutual information between X and X hat. And actually this will give you the number of bits you need to do the compression, right? It's kind of intuitive, but actually, all of them are true. Okay, so we're going to show that later mathematically. Okay, very good. Okay, and then, so because we said mutual information is commutative, right? And then we can write y given y and x. So that's equals to what? Hy minus hy given x, right? Okay, therefore we could conclude these two equations, these two quantities are the same, right? And did you remember that? Right, let's go back. Right, that's exactly this. right? As we said before. Then we prove that, so this and that are not equal in general. Okay, the reason they are true is because, so this is nothing but the mutual information, right? And to be precise, so this is yx, and this is ixy, right? Okay, great. Yeah, any questions? No? Okay, great. Yeah, the math so far is relatively okay. Okay, and now let's derive something else, right? So basically, let's say if we have a mutual information, x and y, and we know that this equals to x and minus hx given y, right? And as, you mentioned before, right? So how about the joint entropy, right? Joint entropy and conditional entropy, they're not, independent concept here, right? Can we get, what's the relationship between mutual information and the joint entropy, right? So we're going to do that, okay? So the way that we're going to do that is as follows. So basically, so for this guy, right? So can we write that as a function of the joint entropy? Yeah, yes, we do, right? So we did it here, right? So hy equals to hxy minus hx given y, right? So by using that, we can write the second guy as the joint entropy minus hy, right? And then if we, remove this parenthesis, then what we're going to get is that hx plus hy minus hxy. Right? Okay, great. And obviously, this is kind of very important formula, right? But if we go further, you can play around with it, right? If we go further, so if we take hy out, right, and then we can minus hxy minus hx, right? And then we can see that. So this guy is equal to what? Hy given x, right? And again, so we reach our conclusion before this equals to hy given x, and that equals to y iyx, right? So we can derive our previous result, right? But yeah, you can play around with it, okay? But what is kind of interesting is this formula. So maybe use, so this and that, okay? So ixy equals to hx plus hy minus hxy. What do you think about it? Did you see anything like that before? Yeah, what? It's like
base upside down.
Base upside down?
Yeah, like
oh yeah, you can imagine that way,
yeah.
But there's some like more graphic pictorial. Exactly, Venn diagram, right? So let's say if we have something, let's say this circle represent hx, and then we have another circle represent hy, right? And the joint of these two circles represent hx and y, right? And let's maybe pick another color here, blue. Let's say this part, okay, that is hx given y, right? And this part is hy given x, right? Because still here is hy, right? And then the mid part is mutual information, right? Yeah, I hear that. Very good, right? So you can, so it doesn't mean, it's for set, right? So, but it doesn't mean, it just, so they represent a set, right? It's just a way to help you to remember it, right? Kind of, because we have so many quantity here, right? Mutual information, have an entropy, conditional entropy, joint entropy, right? So we need to remember the relationship between all of them, right? This is a good way to understand the relationship, right? If you know this figure, then you should remember everything. Okay, very good. That makes sense? Yeah, okay. Okay, so if no question, yeah, let's consider a special case of mutual information, right? Let's say if X and Y are independent, right? X and Y are independent. Yeah, this independent basically means statistically, right? Or SI, statistically independent. Okay, the reason I'm, kind of emphasize on that is that so statistically independent doesn't mean logically independent. Does that make sense? That makes sense? Right, so two random variables could still, depend on each other if they are statistically independent. Okay, it's kind of weird. We're going to cover that later. For example, let's say, yes, two mathematical, but x plus y equals to z. Okay, so clearly their x and z are dependent, right? But I can give an example showing you that x and z can be statistically independent, but this formula still holds. Okay. So who can give me an example of that? Right, I can say that, so this holds and xz, they are statistically independent. Think about that, right? See whether we can come up with an example or not. Okay, anyway, so it's not so important now, but what we want to emphasize is that, okay, let's say x and y are statistically independent. So by the way, so this basically means that pxy equals to px times py, right? This is what we mean by statistically independent. Okay, so if that is the case, then let's compute our mutual information. Mutual information x and y, so that equals to hx minus hx given y, right? So because x and y are statistically independent, right? So this, in other words, this also means that px given y equals to px. Right, therefore, so this guy will just equals to hx, right? And then this equal to 0, which kind of makes sense, right? So if y is independent with x, then knowing y will not tell you anything about x. Does that make sense? Sort of. Okay, so just one more thing I want to mention here is that, so mutual information is not a good metric to measure the dependence between x and y. Okay, so if mutual information equals to 0, so later on we're going to show that, so it's basically equivalent to this formula holds. It's if and only if. If this is true, then this is true. If this is true, then this is true. Okay, so this, from here to here is straightforward, right? But from here to here is not. Okay, but we're going to show that later. So basically, it means that if mutual information is not 0, but a very small number, can we say that x and y are not so dependent? That is no. We cannot. Okay, the only thing that makes sense is when the mutual information is 0. Okay, when mutual information is not 0, although it's epsilon, very small number, then we cannot say, okay, so let's say if your epsilon is bigger than my epsilon, then your x and y is more dependent than my x and y. You cannot say that. So we can give you counter examples on that, right? So that's why information theory is kind of tricky. So there's always something that's counterintuitive, right? The main reason is that the mutual information, is a metric of the reduction of uncertainty in terms of bits, actually. Okay, it's like by knowing y, how many bits you know. But this how many bits you know cannot be translated to how much dependency between X and Y. So they are totally different animals. Okay, but many people think they're the same. Okay. All right, so now let's see what time. Oh, we're out of time. Really? Okay. Yeah, I'll see the next lecture probably. We'll just have one format to go. Yeah, but it worth to talk a little bit. Yeah, and then we'll talk about relative entropy. Okay? Yeah, thank you.